Start up again. One more thing with this source node curve. We had the source looking something like this, and then the 20th floor was something like this. So that was load, and this one was source. And here we are talking about operating points. We are balanced between source and load, so yes, they will be operating points. The question is, are they stable or unstable? Look at the first one, for instance. If you reach this point exactly, you are in balance between the source and the load, everything should be okay. So you should be able to run at this speed, given this torque, for as many days as you like. But see what happens. If you go a little bit to the left, here, then your engine, your source is too weak. So you see, you have a small arrow down here, meaning that if you go a little bit away from this point to the left, your source is too weak, then the system is going to slow down and he will move further away from this point. If you go on the other side, your source is stronger than the load. Then you have additional energy, you might think, additional torque. Then he will speed up the system. Then he will continue to move away from this operating point. So this one is an unstable operating point. What about this one? Well, here you will now get the opposite effect. You go a little bit to the left. Then your source is stronger than the load. He will accelerate up again, and he will move the rotational speed back to where you started. Or if you go a little bit above this point, to the right, a little bit too much, then the load is stronger than your source. You are lacking energy here to keep this speed. Things are going to slow down, so he will push you back again. This is a stable operating point. The problem here, of course, was that you can't never reach this point. If you start from zero, you can't get anything to move. So that's a problem. But we will come back to this example later on. So stable versus unstable operating points. I showed you the Inter-P1 function in MATLAB. Yes, that's a very convenient tool to create a continuous function with a set of data. Another way to do it is using polyfit, where you can choose a degree, any degree of a polynomial to describe a curve. So here I've chosen just a second order polynomial. Then the PM here will give back the power, no sorry, the coefficient for the x squared plus x and so on and so forth. So I can show you how this one looks. Quite nice actually. So there you have the third, the 10th, 20th and 30th floor. You have the source, the motor, the blue line. And I even have found the maximum power, the point where you have the absolute maximum power, should be here somewhere. And a constant power curve, well, that was a hyperbola. You just touch that at this point. So how to find this point? Well, in the program here, since I've used polynomials, then you have direct expression for this curve. So here you have something like the source is now given as m as a function of v dot equals, and then you have actually an analytical expression for them using this poly idea. You have the argument v dot squared plus v dot plus a constant if necessary. So you have an analytical expression, then you can easily find this function here, and then you want to find the maximum power. Okay, then you take the derivative here with respect to the rotational speed, find an expression for that one, and then you demand this one equal to be 0. Then you will have the maximum power. Another way to find it is make this make a graphical plot out of this one. How will he look like? Take the product of these two for the source and characteristic only. Well, he will look something like this. V dot here, and now we plot power, not torque but power. How will he go? Well, you start here, you have torque, but you have 0 rotation, so he will start with 0. Also here, you have no torque, a lot of rotation, but no torque, so also 0. And then the curve, he will look something like this. Then it's fairly easy to find what's the maximum power, at what rotational speed do we find the maximum power. That's another way to do it. Okay? So that was just for a show. In the textbooks, chapter 2 and so on, you will find some of these guided problems. They're sort of examples, but with a good solution some pages afterwards. So if you wanted to sort of have an illustration of any theory, you search for these guided problems. They can be pretty okay. So here have a complex problem, guided problem 2-2. Then you have some other problems, and then solution to the guided problem. So that's these guided problems can be quite okay. Now we jump to generalized forces and velocities. 2. Generalized force and velocity. Force, velocity. What we are going to do is to create a table, and we are going to create it many times. So you can always read this part here if you like, but what we are aiming for is table 2.1. 2.1. First we do this generic force and velocities. Generic. We will have the action, the motion, that will be, we call it a velocity, but it doesn't have to be a velocity. It's a sort of the dynamic motion in our problem. So generic, we are talking about flow, which then is donated a Q with a dot above. in some textbooks you will find a small f for this flow variable. So what will the flow be? In mechanics we are talking about velocity. Fluid mechanics, we are talking volume flow. Electric systems, you have the current, a lot of electrons moving around. For rotational systems, we have this phi dot. Why the dot? Why the derivative? Well, we come back to that later. So the book only uses q dot. If you like, for your own convenience, you can use an f instead, if you prefer. Up to you. Next, the force. That is what we call an effort. Doesn't necessarily have to involve any motion or dynamics, but it's sort of a driving thing into our system that can produce motion. And for the effort, we will then have a small e. E for effort. So this means when you have a power bond like this, a half arrow, you will always put the flow down here, the q dot, and the effort up here, always. Or if it goes this way, okay, q dot to the side where you have the half arrowhead, and the effort on the other side, always, always. This effort, some people also use here a small p with a dot above. Now don't mix the symbols. This large curly p, that's power, something else. Small p here, that is something else. It's the time derivative, or not the time derivative, sorry. If you time integrate this quantity, you will get the effort. So both flow and effort, they have sort of two separate ones. So we could have used, instead of E, we could have used a P dot here and a Q dot. Instead of the Q dot, you could use an F. I don't really care. As long as you know what is what, then I'm happy. So just a notation anyway. So, okay, let's now set up this table 2.1. We start with the generic. Then I want mechanical. Translatoric, meaning just back and forth, straight line motion. We will have mechanic rotational systems. We have fluid systems. And we have electric systems. That should be enough to get things started. Here I want the E for effort. And then I want the Q dot for flow. Then I want not the Q with the dot above, but just Q. Hey, what's that? Then you need to do some integration of this Q dot quantity to get the Q only. What will it be? Well, we can start here. The generic here, it's E or P dot if you like. For the flow, that's just an F or a Q dot. For mechanical motion back and forth, what will the effort be? Well, that is a force. And the motion, that should now be velocity, v. And velocity, well, that's the same as the time derivative of position. Meaning, what will q be if q dot here is the velocity? Well, that's just the x. So in this one, we have to call displacement. So for mechanical systems, the q alone, sort of time integration of this, will just be position x. Okay? And finally, we are going to need, for this effort, time integration of E. That should now be just small p. Time integral of E dt. As this q is time integration of q dot dt. So what is the time integral of force? That should be the same as momentum, mass times velocity. So in some physics books, they use P for momentum. Of course they do. So that's why we need a P there as well. Okay, so now we can start filling in the rest here. For a rotational system, the effort we have seen, that is torque, and the flow, that is angular velocity, rotational velocity. What's the displacement? Time integral of a rotational speed. That will now just be an angle, phi. What will the time integral of this guy be? That's a trick question, isn't it? Can you, if you recall from basic mechanics, you have Newton's second law of motion saying mass times acceleration, that is the sum of all forces. So the time integral there, well, that was just the momentum, or you can write it like this if you like, the t of mass times velocity. So the time integral, yes, is mass times velocity. Then you have the angular momentum theorem there. You have a lot of torque that is operating on something, on a mass. It starts to rotate. Well, what is the law here? The sum of all torques acting on something will be the change, rate of change of, what should be here? You don't remember? What's the English word for it? It's the same as the Norwegian word. It's called spin. So you will have the I here representing the rotational mass multiplied with an omega rotational speed. Some people call this just H for spin. So you have something that rotates. If you expose it for a torque, you will spin faster, the spin will change. So here you will have H. That is a spin. Fluid mechanics. We have already seen the flow. That was the volume flow using a large cube for the volume flow, cubic meters per second. The effort in fluid, that is the pressure, like that. Now let's just check while we're at it here. Check here. When you multiply effort with flow, you should get power. Okay. So this one, torque multiplied with rotational speed gives power. Okay. Maybe not. How should we think here? Well, we can go to the mechanical translatoric. You have a force multiplied with a velocity. Okay. Is that energy per time, is it? Well, if you write it like this, you have force times a distance divided by time. Then you should see it more easy. Force time displacement, that is energy. That's joule for you. And then joule per second. Okay, now we are talking power, watt. What about fluid? Say you have a pipe here, and inside this pipe here we put in a pump of some sort. Then we will have a pressure difference, an increase in pressure through this pipe system if it's volume flow going through it. What is the power here? Well, the force you can think of as pressure multiplied with this area. So we write this pressure change multiplied with the cross-sectional area inside the pipe. This will now be a force. Force should be multiplied with what? With a velocity. Well, that must be a velocity for the liquid then inside the pipe. Okay, but A multiplied with that velocity, area times velocity, that is the same as a volume flow. Yes. So the product here, pressure times volume flow, will give you power. So it's okay. Then we have a question here. Displacement, what will that be for the volume? The time integral of this guy. Time integral of a cube. Okay, this is now cube. What's the time integral of that one? Area, that's just an area. So you have area multiplied with a distance, x. Well, if you have a distance here and then a cross-sectional area, you will have a volume. I use a large V with shoulders just to say it's a volume. Finally here, and this is now getting confusing, we have a small p here. That was for the effort. We used a p dot. But here in fluid system, a small p means pressure. So don't mix the different p's here. It can really get messy. So here, I want to have a time integral of pressure in a fluid system. So now we are talking pressure as the effort. Nothing to do with that this P here, meaning this time interval. So what is this equals? I have absolutely no idea. What's time interval of pressure? It's not a physical quantity that can help us with anything, so forget it. We don't need it. Finally then, electric systems. The effort, driving force in the electric systems, that must be the voltage, large U. And the flow, that's the current, large I. I wonder if the book uses a small I there. Yeah. Small I. I use a big one, but not that important. Fluid. The book also here talks about the microbonds, which you can forget. Not important. We never use it anyway. So here you have the first version of table 2.1. So I have expanded it a little bit. Here we need now the time integral of the flow, which is the current. What's the time integral of current? So then you have a bunch of electrons, don't you? So you have a charge. No, not that we need it for anything, a charge. C, or also I've seen Q, large Q for charge. And also here, finally, the time integral of the effort, time integral of the voltage is not anything physical that we can use for anything, so just forget it. So that is table 2.1 for you. So copy it down and remember it and use it in any problems. Because when we now are going to use bond graphs, we will have source, we will have load, resistance, we will have junctions, we will have different elements on each side of these bonds. But always we will use these letters here for effort and flow. Because we are going to mix up a problem. Part of the problem will be mechanical, another part will be fluid, and a third part can be electrical. So we mix a lot of different energy domains in the same problem. So we use the generic symbols all the time. E and F, and here then Q and small p. So we use these letters for any problem. Then in the end, when we have solved everything, then we can sort of use this table 2.1 to translate back the different physical quantities. So we will have here a whole bunch of Q's as time goes by, finding this function as a function of time. And then we can say, okay, what kind of problem did I have? Well, it was mechanical, translatoric. Then it's a position. X as a function of time. So what these actually represent, you see from this table. So it's a quite essential piece of information to keep quite handy. Nothing that you need on the exam. On the exam we will have some formula sheets, so this table will be there as well. So you shouldn't, you don't have to remember it, but for now, put it on a piece of paper and bring it with you. It's not the entire truth necessarily, but it's something here has been modeled. The mechanical, they are quite okay. Also the electric, the fluid may be a little tricky here, Sometimes we want to have more than just the static pressure here. Maybe we want to have the dynamical pressure here as well. So that's an option. But in general, we skip this one. Normally, it's the pressure that is important. The dynamical pressure doesn't change much in the system, so normally we forget this one. But just be aware, it might show up. Yeah. So in here, generalized source and sink and resistances. We can just make a note of that for the end here. Source and sink and resistance. So in our sprinkler example, we had a power supply and a motor. That was our source. He could produce something that rotated, and he could produce something with a torque. Definitely, yes, a source. So for sources, we use an S. Then on the other side, we had a load. Load, you could say, is a source with a negative sign, meaning a sink. That could be one way to do it, but no, we are not going to do that. We are going to call him resistance. So instead of load, we say resistance. And resistance, that is large R. So our bone graph should actually have looked something like this for the example with the sprinkler. With a water sprinkler. And as you see, effort on top and flow under. So normally you don't even write these. E here and an F down here, or a Q dot as the book likes to do it. You don't write them, you don't need to, because you know they are there anyway. Effort and flow. For sources, we now had the privilege of seeing an example for a real source. Real source, we have the characteristics. Which then was a data curve, something like this. For the rotating system, then it's torque versus rotational speed. If it's a source for an electric, it will then be voltage versus current and so on. Some curve giving the real source behavior, you might say. What we are going to operate on is ideal sources. Ideal sources. And we have two types of ideal sources. One source will be an effort source, another will be a flow source. So we differ between those two. SA, that is an ideal effort source, while an SF is a flow source. And how would they look in the same diagram? Rotational speed and here torque. If you had a perfect ideal effort source, he would then be able to provide you with a certain effort regardless of the rotational speed. So here you will have a perfect effort source. He can provide you with this torque no matter what. You don't care how fast it goes or if it doesn't move at all, just perfect. Gives you a certain torque, no matter what. The ideal flow source, well, he's different. He can provide you with a certain rotational speed. He don't care how heavy it is. He will give you that speed no matter what. So a flow source, he will look something like this. So that is the perfect flow source. And a perfect flow source, of course, can be very hard to find in real life. A perfect effort source, that is possible. That's possible. How can you find a perfect effort source in a rotating system? You take a wheel here, and then you have an axis here, something like this, and on this wheel you have a thread, and here you let the thread go down, and then you put on some weight here. So due to gravity, mg, this will now provide a torque on this axis here, depending on the arm, R. So here you will have a torque given as the force, gravity, multiplied with the arm. And you will have the same force whether he rotates or not. The gravity doesn't change. If you move or not, it's the same, it's a constant force. And here now constant torque. You can have the same effort, ideal effort source in translatoric problems. Things moves only in a straight line. Of course, gravity is the same force, regardless if you move or not. So here also gravity will give you a perfect ideal source. So ideal, meaning then is independent of the other variable. Effort can give you a torque regardless of rotational speed. Is independent of the speed, while the flow source is independent on the effort, on how heavy it is. He doesn't care about that. So for effort sources, we have a small e, flow sources, we have a small f. What about our example that we have here with this source load example, the sprinkler system? The S was given with a real source, not an ideal source. We had these characteristics. And what should we call him? Well, actually, we just call him an S. He's not an effort source, he's not a flow source, he's a real source. Then you just call him an S. I mean, this curve, it doesn't really match any of these two. You might say, for this area here, is fairly straight line. So in this region, yes, he could be treated as an ideal effort source. But it's not a nice description of the real thing. So you should keep him as a real source. We will work with ideal sources later on. The sink, you can just forget, we don't use it. Instead of sinks, we will always use resistances and R instead. So you have here some examples. Gravity for perfect or ideal sources. For a fluid source, provides you with a pressure. Could be a big reservoir. Then the pressure is rho GH, the depth. And ideal effort source for in an electric system, battery. The sinks, as I said, just forget them. We don't use it. And here, for he doesn't have it here. The flow sources, they are not really so easy to find in real life. These are the effort sources. Yes, they can be found, but perfect flow sources, not so easy. Not so easy. So we still use them. It's easy to play around with, but in general can be hard to find in real life. Okay. We will then continue next week with resistances. Now on Friday it will be guidance for exercise 1. And we are to be in room number F2. Any questions? Then we stop here.